I've decided to start with problem number 27. The problems this time around on chapter 8 that was given by Dr. G as homework. They are not particularly hard or involved. However, each of these problems have different parts or principles that you need to know in order to solve. Okay? So let's start. Problem number 27. What I will do afterwards is I'm going to bring you guys to the board, and then we will go over the other problems. Hopefully we can do quite a few. So this is the bone at the bottom of your mouth. Okay, and then of course in my very dull way of drawing. Okay, so this is the top half of your mouth, and then this is the bottom half of your mouth. So when you bite into something, let's put a chunk of food. You don't want to eat something like this, right? The point is this. When you're trying to bite into this, every action has an equal and opposite reaction, right? Newton's laws. So there will be a force applied downwards. Okay. That's why you don't want to bite into things that are really, really hard. Okay. So we are going to ignore the part where the force applied on the food or the chunk of food, because that's not what we are really interested in. We are interested at the forces acting on the bottom half of the mouth. So in other words, you have a force going down like this, and then that's given to us, and it is given as Fc, and then on the picture we have two other forces, and then this is T, and then this would be R. Now of course this is because of the muscle. Okay. Now there is a pivot point also because of a muscular connection at right here, right? So now what we are going to do is this. First, let's put all the data that we have. So what's the force that's acting down right here? Nobody has the books up. Bring the textbooks up, please. Before we discuss this, we really need to go over the problem, right? Problem number 27. Find me the numbers.
50.
I'm sorry?
50 newtons.
50 newtons. And then of course, that's what's given to us. We are getting the distance, horizontal distance. And tell me, what is this?
7.5 centimeters.
7.5 centimeters. What is this?
3.5.
3.5 centimeters. Now, when we talk about motion, there's two types of motion. Since we discussed a lot about translational motion, so in other words, things are moving. Now we are at a point that we will talk about rotational. Now sometimes things just rotate, they don't go anywhere. Like think about a merry-go-round. You feel, of course, if you are at the periphery, or in other words, circumference of the circle, then you are moving. But in reality, you are not moving, because you come to the same place again and again. So that is a circular motion. Whereas if you drive your car, and you start driving. That's translational motion. Sometimes they are interconnected and sometimes they are together. For example, if you think about your car, the engine has a crankshaft and you have a gearbox inside. And there's a lot of things that are rotating inside the car, in the engine, right? But the car itself is moving forward. So it's a combination of both rotational and translational motion, two of them together. However, when we consider motion, most of the time it's not that complex. Okay? So first off, since we have rotational motion requires a certain important part in order to start. For example, if you think about this box, right? Say this is my weight on the table. So in order to start this motion, you need to lift this up, right? So in other words, what I'm doing here, in order to move it up, what I'm giving to this object, I'm applying a force. And when I apply a force, this accelerates. In other words, changes the velocity, and that's why it's moving up. Right? So now, same principle applies for torques. Or in other words, rotational motion. In rotational motion, we require a torque in order to start the rotation. So, let's say, in this case, I have a question. Is this moving anywhere? Is this rotating or moving? Usually it does rotate and it doesn't move. It's rotating but not moving. Okay? So in other words, if it's not moving, what can you say about the forces? Sum of the forces have to be equal to 0. Now, if it's not rotating, what can we say about the torques? Rotational motion requires torques. So what can you say about the torques if it's not rotating? It's going to be 0. All the torques, the sum of all the torques have to be 0. Rotation requires torques. Translational motion requires forces, in other words. In other words, to start. Okay, once you start going at a constant velocity, you don't need to require any force. I'm just saying it at the beginning. Now, in this particular case, this is what we are going to do. We are going to start applying the torques first, and then we will apply the forces second. So now these are my points. I'm going to mark the points. B, C. Since it's not rotating, I'm going to say sum of my torques is equal to 0. Now, there's a funny symbol. You guys belong to all kinds of fraternities, sororities. You know the Greek alphabet inside out, right? Pretty much. This is tau. Tau means, of course, a symbol that we usually used to name torques. Okay? So this is the sum of the torques that is equal to 0. Another thing that you have to remember is that whenever I have motion going upwards, I would say that that's positive direction. For the torques, the same principle applies. There is two rotational directions. Here, if your rotation is towards clockwise direction, I'm going to say it's positive. If it's counterclockwise direction, I'm going to say it's negative. Okay? All about rotation. So now what we need to do is we need to find out about our torques, how they work. Now, first thing I want to say is that since this is not rotating at all, I can assume that, in other words, when I calculate the torques, I can say any point as my pivot point. It's not really rotating at this point because it's stationary. Now, why I'm saying it's stationary? Because what happens now is like whoever is doing this is biting into the food, in other words this piece of meat, and just holding it. So the forces are balanced, torques are balanced, mouth is not moving. All the torques are balanced at this point. It's biting into the meat. That's it. Okay? So now, let's see. I'm going to say my pivot point is right here. And I could have easily taken my pivot point to be right here or right here. Now when I select my pivot points, however, you have to be careful because now this is given to us. These two are not given to us. We want to use what's given to us. So therefore, I would not want to go and select this one. When you solve few other problems, you will notice this. So I'm going to select this point as my pivot point. So I'm going to say it's above B. Okay. Now, let's try to kind of put our torques. Okay. Torque is defined as a force times the vertical distance to the force from the pivot point, right? So now if I look at this, this is my pivot point. Distance from the pivot point to this force is how much? How much is the distance from the pivot point to this force? 7.57. Now when we measure this distance, we measure it so that this distance is the shortest distance between the pivot point and the force, 1. And this distance has to be normal to the force. Okay? Sometimes we have forces going at an angle, then we have to resolve that. And I'm going to let one of you come and solve the first problem, which is going to deal with exactly that. Okay, so now what do? We have the force Fc. I'm going to keep the symbols, so it's a little bit of writing, right? And then of course 7.5 centimeters, force times the distance to the pivot point, and I'm going to directly write this as meters. Now, my question is that torque, the rotation happens this way. If I take this as my pivot point, the rotation happens this way. Is the torque is positive or negative?
Positive.
It's positive. Is it?
No. Then negation. This is going counterclockwise.
And I took this, all the clockwise rotations as positive. This will rotate this whole arm, or in other words this bone, counterclockwise direction. So what is the direction, or what is the sign of my torque? Negative. It has to be negative. So I'm going to put a negative sign. And then, what is this? I have another force. Now the force going through the pivot point has 0 distance. Therefore, there is no torque because of this force. If it is going slightly shifted away from the pivot point, guess what? I have to calculate the torque. But this is directly going through the center of the pivot. So in other words, I don't have to calculate that. In other words, it will give me 0. That's why I'm not writing. Now, this one, this is another force. This force will try to rotate this bone in this direction. Can you see that? Force is working down this way. So in other words, it will rotate this way. Now that torque, is it positive or negative?
Positive.
Positive. So that means I have a positive torque. And then I have, what's the distance? Vertical distance is this much. That's my distance. I said that I need to be 90 degrees to the force. And this is my force. The line of the force. Forces are directional. So in other words, it is a direction that counts. When when I write a line, that is along the line is where we have the force. So if I measure the distance from the pivot point B to the force, it has to make 90 degrees. So this is the distance that matters. And that is why I'm going to have to use this distance, which is that. Not this. This won't help me. Okay. This is my force, 90 degrees to the force, right? So that means what? I have my force R times. Again, I'm going to write this in meters directly. The sum is equal to 0. What's our unknown? What's our unknown? R, because Fc is known, right? So I'm going to isolate R. I'm going to take all of that into the other side. I have Fc times 0.075 meters divided by 0.035 meters. Now this is 50 Newtons. Find me a number. Meters to meters cancels out. All I have is Newtons. Find me a number, please. 107, yes. So I'm going to write what we found. R equals 107 Newtons. Everybody's done writing? I'm going to erase this and start. Now actually I may be able to use the bottom half. So now what do we have? We have to consider the forces. We already took care of our thoughts. So now what we are going to do is we are going to look at the forces. Now this is not moving, especially up and down. That's where the force is acting, but it's not moving up and down. The sum of the forces is therefore has to be 0. Now all the forces going up I will take as positive. Okay, you always have to designate what direction is positive, what direction is negative. So let's start looking at our forces. We have Fc, we have T, we have R, and the sum should be 0. Now, question. What forces are negative, what forces are positive?
Fc and R are negative and T.
Fc and R are negative, okay. Okay, go ahead. What else?
T is positive.
T is positive. Sum is equal to 0. Okay. What's our unknown? T. That's exactly. So T, we take both of these into the other side, and R, Fc is 50 Newtons plus 107, R is 107 Newtons, altogether 157. We found R to be 107. That is why I can substitute 107 to R. That's how I got this. Good? Okay. As long as you follow, I'm okay. Okay. I think I'm going to do one more and then I'm going to move on with you guys. I'm going to let you write the course pretty much. Okay, let's see the last one. Problem number 61. Okay, what we have is a disk. And this is rotating. Okay, and we have a radius given to us. I'm going to put capital R. 1 meter. Mass of the disk is what? 10 kilograms. What's the angular velocity? Initial angular velocity? I'm sorry? 7 radians per second, right? 7 radians per second. And of course, somebody is going to drop a probably a droplet of clay or something that really gets attached. And the mass of this is, what is that? 0.25 kilograms. And also, the distance is also given to us. This is at a distance of d equals 0.9 meters from the center. So, what is the question? We are supposed to find the change in angular velocity when you put the droplet down. So the droplet comes, piece of putty comes and hits the disc, gets attached. Okay. Now this is totally inelastic because things are basically attached to it. Okay. It's not elastic at all. Just remember. So whenever we have such scenarios, we cannot apply conservation of energy. Okay. The law that we can apply in any of these cases is conservation of moment. Works everywhere. Jack of all trades. Can work with it anytime. However, we don't have translational motion. We don't have anything moving. It's a spinning disk. So we have rotational analog. In other words, something similar to angular momentum, something similar to linear momentum, which we call the angular momentum. Okay? So angular momentum is given by I omega. And you guys have done this in the class, I think. Have you? Not yet? Or have you started that? Angular momentum. Yes, you did. So now, what we have is the conservation of angular momentum. In this case. Oh, actually, it's better to write this like this. Initial. Final force system. Okay. So let's look at this. Now, omega is given to us initially. So I'm going to get rid of this summation symbol because, let's be honest, we don't have a big system of rotating particles or objects. So what we will do is, I will keep this as it is. So omega before and then phi. Now this is what? This is the initial. Rather than putting 0, let's write I. I is for initial. What is this? Is it given to us? This is I. This is the initial angular velocity. Before we drop this putty onto the disk. So the disk is spinning, okay? Disk is spinning. And we get this. Let me show you this. Right? Something like this. So we drop the droplet, get stuck, and keep rotating. Okay. So we had initial angular velocity for this disk, and then as you drop the putty, which gets stuck on the surface, the angular velocity will change because of the conservation of angular momentum. This is what's going to happen. Okay. So what we are going to do is this. We're going to apply conservation of angular momentum. However, we have to find these guys out. This is given to us. We need to find this. We need to find this because otherwise we have 3 unknowns. We cannot solve this. So we need to find the initial moment of inertia, final moment of inertia. That is our focus at this point. So let's find the initial moment of inertia. Initially, the drop or the putty is not there. So it's just the disk that's spinning. So for a spinning disk, the moment of inertia is equal to 1/2 mr squared. You have that in your formula sheet. Okay. So now we know this. Let's plug in the numbers. What is the mass? 10 kilograms. And of course, r squared is 1. So much easier, isn't it? There's no square root, right? It's just 5 kilograms meter squared. Now we need to find the final moment of inertia. Okay. Now, have you guys done the theorems of moment of inertia, transformation of moment of inertia, shifting? Just slightly, I think, right? Because you can add moment of inertia. Okay? So for example, what I'm going to do is this. This is the moment of inertia of this disk above this spinning axis. All we have to do is to figure out the second moment of inertia is to add the moment of inertia because of this putty. That's all we have to do. So what I'm going to do is this. To find this, I'm going to keep my initial moment of inertia and I'm going to add the moment of inertia that's coming because of this. How do I add that? All I need is mr squared. So m is simple m, and then I have d squared, and this is what I need to add. So numbers wise, I have 5 kilogram meter squared plus mass is what? 0.25 times 0.9 squared. Find me the total final moment of inertia. How much? 0.2 over here, so I should get about 5.2, I think. Is that right? Because this is like 1/4. 9 squared is 81, decimal place here. 4 times 2, and I can put 2 here. So this is going to give you 0.202 at the 5.2. So you have nice calculators, you don't have to do that, right? So 5.2. So that's the moment of inertia after the putty being dropped and getting attached to the disc. So that's good. So now what? Now we have to apply to this formula. That's all we need to do. So let's write the formula right here. Omega I equals I final, moment of inertia finally, angular velocity final. So only thing that we don't know is this. So isolate this. So I have I, omega I divided by IF. Let's substitute. What is I? Moment of inertia initially 5 kilograms meter squared. Angular velocity is equal to 7 radians per second. And then I have the final moment of inertia, which is 5.2 kilograms meter squared. And then find me, what do you get? Any questions that you don't follow? Everything's good? Sherry? Okay. So let's see. We have, what do we get? 6.73. And that would be radians per second, because if you look at this cancels out, this cancels out, I get it. That's exactly what we want. I want you to see something here. In linear momentum, remember, this is what we had for linear momentum. Always connect things, guys. If you look at this, this is what we had for linear momentum. Guess what? Angular velocity, linear velocity. Moment of inertia, mass. They correspond to each other. This is our linear momentum. This is our angular momentum. Angular momentum is given by L. Okay? So look at this. I never remember these things separately, to be honest with you. I always remember this and then I build the other one immediately. Because so much easier. Less things to remember. We have more than enough things to remember, right? So that's the bottom line. Try to remember the most fundamental things and build the other things. Okay. That's the idea. I'm gonna let you guys start. I'm gonna stop this, and then